First of all, I want to say it's a real pleasure to be here. You know, I am from up north. It's very cold, and I like beaches. I don't see much of them. I'm hundreds of miles away from any coconut, so it's a joy to be here, and I look forward to meeting you. I just got in last night. So I want to talk about neuronal avalanches and criticality, and so let's get started. So basically, I want to talk about three main things. First, I need to learn how to use this. Let's see this. Okay. All right, so first thing is I want to talk about what the critical point is. And I know that not everyone here is from physics background, so some people from biology. So I want to make sure that I explain what that is. So I'll give a simple example using the Ising model. It's a model of a magnetic material. We'll talk about what it is and what the properties are when you're near the critical point. Next, I will talk a little bit about data from neuroscience. Some data from recordings that we have made, and then talk about recordings that other people have made as well that make this sort of a good analogy, make that a reasonable hypothesis or assumption. And then finally, I'll talk a little bit about why should you care? Who cares if the brain is critical? Well, does it mean anything about health? Does it mean anything about how we can understand how the brain works? These are the things that I will talk about. All right. The critical point. So I'd like to mention that there are lots of people working on this, okay? I am one of many people who've done lots of work. Mauro Capelli is also speaking right after me. He will talk about things that are very important in this area. Some people that you may or may not know of, Dante Chialvo, he's done a lot of work on criticality. He's worked with Per Bach. Stuart Kaufman had ideas about criticality in biochemical networks. Klaus Linkenheier Hansen, he works on humans. Greg Worrell has also worked on epilepsy. Dietmar Plenz is my former postdoctoral advisor. He's done a lot of work on this. He's now working on humans, looking at avalanches and criticality in human data. Jack Cowan is a theorist. He has developed ideas about this. Ed Bullmore does a lot of work on humans as well. Lucia D'Archangelis, she's a theorist who is working on ideas about this. And Bill Bialik is also a theorist working on ideas related to this. So there's a lot, and I haven't even listed everybody, okay? So there's lots and lots of people working on this area. Just wanted to point you to their work, if you're interested. Okay, so being in the land of soccer, or as you say, football, right? I want to start with the collective emergent phenomenon that you all understand, right? Now, they call it the Mexican wave. In the United States, they call it the Mexican wave. Is it really the Brazilian wave, right, where everyone stands up and sits down in the football stadium and it goes around? I don't know where it started. But this, it's Mexico? Washington University. It was a bunch of physicists sitting in a stadium, right? And they said, okay, stand up. All right, everybody go to the bathroom. You first, then you. Okay, I don't know, but this idea of a big thing moving across the stadium, that's a perfect illustration of an emergent phenomenon, okay? So what do I mean by an emergent phenomenon? It is something that is more than the sum of its parts. So if I wanted to study this, I could take an individual spectator, bring them into my office, sit them down in the chair, and say, sit down, stand up, sit down, sit, you know. I could understand maybe a little tiny bit, but I would miss everything if I only saw one person. The way I have to understand this is when I have many of them interacting together. Then I see how big the wave is, how fast it moves, whether it reflects, what happens when two of the waves come together. Do they stop or do they pass through? All of these properties I cannot understand by one person. I must see all of them interacting together. The whole is more than the sum of its parts. So this is a simple example of an emergent phenomenon. You have to have lots of elements, people. They have to be interacting in some way, and there need to be some rules for this interaction. Okay, here's another example. How many people have seen these movies of the starlings, the birds flying? Anyone? Yeah. Oh, they're beautiful. So lots of birds come together at night, and they are looking for a place to roost. And as this giant mass of birds is traveling, what happens is a pulse can travel from here to there and then come to the other side. So even though this flock is moving, within the flock you have little pulses, kind of like the Mexican wave. And these pulses are not pulses of birds moving, they're pulses of birds changing their orientation. Their angle changes a little bit, and that causes another bird to change its angle. And you can see that flow across the whole flock very quickly. This is another example of an emergent phenomenon. The individual bird, you cannot understand it, how the phenomenon works, but you must get all of them together. Then you can see what is going on. Okay, what about this? Lots and lots of neurons. Now, I don't mean to be insulting, but one single neuron is very stupid. It's not very smart, right? What can it do? Okay, my apologies to anyone who studies neurons, okay? But what I will say is, it does have some impressive processing capabilities. It does. It's interesting. And maybe it takes a whole computer to simulate one neuron. But the real power of the brain comes from all of them interacting together. They have emergent phenomena, like memories, like thoughts. One neuron by itself probably cannot play chess, right? One neuron by itself probably cannot recognize a face. But many of them working together can produce these emergent phenomena, and ultimately things like consciousness, which is beyond the scope of this talk and probably this whole workshop, right? So what we're interested in is how do neurons collectively work together? And what I'm going to tell you today is a very simple example of cooperative or collective interactions in neurons, this idea of criticality. And once we understand that, the individual neuron does not become so important. It is the rules that allow them to interact and the structures that emerge from that interaction that we will be interested in. Okay, so here's where we start to do the physics. And I am told that there are many elves in the audience, right? So what we want is to talk about something called the Ising model. All right, the Ising model is a model that represents a piece of, let's say, iron. Let's say you've got a piece of iron and you have a lattice. And on every lattice site, you have these little things. They're like bar magnets. And if the arrow is pointed up, that means north is this way. So all these things are spins at lattice sites. And what we have is a rule for them interacting. They prefer to point all in the same direction. Nearest neighbors influence other neighbors to point in the same direction. So that's the rule that we have here. So when one of these guys in the center is pointed up, it will influence most of its neighbors, but not all of them, to point in the same direction. Now, I will represent this type of lattice in movies by pixels. A bar magnet pointed up or a spin pointed up is a black square, and one pointed down is a white square. Okay? So, like I said, most of the time they like to point in the same direction. They have nearest neighbor interactions. So there's three regimes that we can have. One, when the temperature is very low, I'm adding no thermal energy. The lattice is by itself. I'm not shaking it. It's just standing by itself. Nearest neighbor interactions dominate, and all of the spins point in the same direction. That's when the temperature is very cold, low temperature. What happens if I heat it up? I start to shake it. If I start to shake it, I add thermal energy. This causes the spins to go in many different directions. Now, in the Ising model, for those physicists, we really only have two states, one up or down. But I'm trying to illustrate here. Also in the Ising model, you only have north, south, east, west connections. But let me just illustrate here with a broader model. These things will point in many different directions if you add thermal energy. The nearest neighbor interactions are still there, but now this thermal energy overwhelms them. And now they do not point in the same direction. So over here, all the bar magnets are adding up. And when they all point in the same direction, this piece has magnetization. It can stick to another piece of iron. So it has magnetic power. Here, it does not. Punk, it falls off. In the United States, we always take pictures of our children and add them. What's the problem? Oh, yeah, right. Okay, thanks. This is a workshop. Okay, so in the United States, we always take pictures of our children, okay? So here's my daughter, and I take a little magnet to stick her to the refrigerator, right? You know, tunk. So that's what happens. I really need this, right? Okay, so that's what happens when this is cool, when the piece of magnet is cool like this. But now if I'm to heat it up, if I'm to add a little flame to it, right? So if I add flame to this, it will fall off, because what's happening is I'm shaking up the magnet, right? And now these things are spinning, pointing in different directions. And so what happens is these guys cancel. This one will cancel with that one. No net magnetization, and the piece falls off. Okay? You understand, right? So that's when things are very cold, and that's when temperature is very high. All right, what happens in the middle? In the middle, just in between, somewhere in between, what you have is you have pockets of order. Here, these guys are pointed in the same direction. I have a domain where these nearest neighbor interactions are causing them all to point in the same direction. But then I have another domain here. These guys are pointed in the same direction here. I have local pockets of order, but I have many different pockets. I have variety. I have a mixture of variety and order. Here, everything is crazy, random. Here, everything is boringly ordered. But here it is a mixture of order and variety. And many people think that this is where complex phenomena reside. And we will show that this is what's going on in this particular model. Also, if you have questions, please raise your hand. I'd be happy to explain or try to explain. Okay, so these are the three regimes. What does it look like? Okay, here everything is subcritical. So when it's subcritical, it's very cold, no temperature. And now what I'm going to do is I'm going to start from this configuration, and I will go in and randomly pick a site, and I will flip the site. I will cause the spin that's up to go down. And if it lowers the energy, if it is the same as nearest neighbor interactions, I will keep it. And then I will go to another spot, flip the site. I will only keep those changes that lower the overall energy. And here, because nearest neighbor interactions dominate, what do you expect will happen at low temperature? Any guesses what will happen? At low temperature, I go in and flip the spins. What will the final state of this thing be? I need to cause you to think. I might call any one of you. Now you're getting nervous. Think, you must think. Be scared. Start thinking, what's going to happen? Well, let's take a look at it. When the temperature is very low, the only thing that matters are nearest neighbor interactions, and all of them will point in the same direction. If I go in here and flip a spin, it will look like these guys, because this area of neighbors is bigger than this area. Eventually, the entire sample will be all black or all white. They will all point up or they will all point down. And that is because the temperature is low and nearest neighbor interactions dominate. That will be the lowest energy state, okay? Now, that's what happens when it's subcritical. Supercritical. So is this low temperature or high temperature? High temperature, good. Got to keep you guys awake. So I'm shaking the lattice very hard. What is going to happen here? Will they line up or will they not line up? Not line up. Okay, let's take a look. Let's see. Yeah, very boring, okay? Totally random. Nobody lines up. Nearest neighbor interactions are still active here, but they're overwhelmed by the thermal energy of shaking the lattice, okay? So now thermal energy way too high, and so you get no order at all. All right, now, here's the interesting case. Here we have nearest neighbor interactions are about the same magnitude as the thermal interactions. Now it's balanced. Any guesses as to what you will see here? Okay, let's try it. It's not random. You see these blobs, right? These blobs are there. They're not static. They kind of move. Sometimes they even stick out little fingers almost and come back. They almost look like amoeba. They almost look like they're alive, right? It's much more interesting at the critical point where you have this balance going on. Things get very interesting here. Sometimes, yeah, if you squint your eyes, you can look at it. Also, clouds look like this. If you look at time-lapse movies of clouds and how they form and disappear, very much the same type of thing. Lots of phenomena like that. Okay, so since we want to quantify this, we want to put numbers on it, let's see if we can measure something here. And what I want to do is try to use this as a model for the brain. We want to argue that somehow this is a little bit like the brain. So how we're going to do that, if these little lattice sites are like neurons, then one thing we might want to know is how do these sites communicate with each other? So what we're going to do is we're going to take a small pixel A, like this, and see how does it communicate with another pixel B, like this. And to measure that or quantify it, we will use covariance. We'll do something like this. I'll call it correlation. It's a dynamic correlation, but it's really covariance. So what is this? Here is the site, lattice site I, whatever its state is at the given moment. Let's say it's either +1 or -1. Here is the average of lattice site I, whatever its total average is. How, maybe half the time it's pointing up and half the time it's pointing down, then the average would be 0. But if for some reason it mostly points up, the average would be positive. So this term right here is really just the fluctuation of lattice site I over its average, or below its average. How much does this differ from its average at any given point? And the same thing here for J. This is the fluctuation of J. To have this C be a positive value, we need two things. One, we need a fluctuation. This needs to be different from its average. And we need both of these fluctuations to point in the same direction. So maybe both of them point up, or maybe both of them point down. So we need fluctuations, and we need coordination. We need these two to point in the same direction. If this is above and that's above, it'll be positive. If this is below and that's below, then negative times negative, it will also be positive. Okay? So two things, coordination and fluctuation. All right, so now let's kind of schematically look at what happens to the correlations over time. Well, what happens when the temperature is very low? Very few fluctuations. So if I were to plot the angle of the spin, let's just say we had an angle, and I looked at it over time, it would not change by much, and they would both be roughly the same. So here, they are coordinated, but there are very few fluctuations. Okay? Coordination, but no fluctuations. What about high temperature? So here, we're shaking the lattice. The angles are pointed in many different directions. Here, we definitely have fluctuations, but we have no coordination. They are not doing it together. Okay? But here, we have a mixture. Here, we do have fluctuations that are bigger than this, but not so big as that, the fluctuations, and they are coordinated. So if you remember that amoeba-like thing, as it moved across the screen, what it would do is it would move across and flip a spin, and then it would flip this spin. And then as it left, it would flip that down and then flip that down. So it causes changes, so we've got some sort of fluctuation, and they are coordinated roughly on the size of whatever that blob was. So here, what we have, if you were to measure this covariance or dynamic correlation, it will be high here, because you've got a combination of coordination and fluctuations. Here, fluctuations, but no coordination. Here, coordination, but no fluctuations. Okay? So it drops, C drops, but for different reasons. And here it is high because you have both. Okay. So now we can plot this length as we go from one lattice site to another. We go across the lattice to a different location. So here, I will randomly pick one lattice site, I will measure this correlation, and then I'll move away from it. This is what happens at low temperature. So what you can see is that there's very little carryover. If this is some value, then these guys very quickly, within 5 lattice sites, it drops into the noise. What happens at high temperature? At high temperature, you're shaking the lattice so hard, again, you don't really get much of this. Okay? Any guesses as to what happens at the critical point in the balance? What will this plot look like? Yeah? It will go up? You think like this? Okay. How many people say it will go up? How many people say level? How many people say down? How many people say tiny? You're not allowed to answer. Neither you. And probably a lot of you know this. Okay, let's take a look. Okay, so you've got the right idea though, right? So it does still fall, but it falls very, very slowly, okay? And it goes about 15 lattice sites before it runs into the noise. So now, this is a simple example of an emergent phenomenon or a collective phenomenon because in the model, we only built connections 1 unit long. One site to one site, only 1 unit long. But here we have some significant relationship that's 15 units long. So it's a very simple example of what happens. The correlation length, let's call it 15 here, is greater than the nearest neighbor length. So that's a very simple example of an emergent phenomenon. And it's happening only at that temperature. When I'm above that temperature or when I'm below that temperature, you don't see it. Okay? So this is just to give you an intuitive idea of what's happening. All right, so we look at the correlations with distance, and we also looked at them with time. Let's now plot this. Here's the correlation length as a function of temperature, okay? Now what happens when the temperature's low, things go into the noise at 5. When the temperature is too high, things go into the noise at maybe 1. But right around the critical temperature, you'll get the correlation length to increase. Now, if this model were really, really large, almost infinite, what you would see is that this little area here would become very narrow and it would become very tall. So now I could take the temperature and let's call that my control parameter. I could sweep it from low temperature all the way up to high temperature. And as I go from low, I would see nothing, 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 nothing. And right at that spot, bing, it would go up to infinity. It would be infinitely narrow and infinitely tall. That would be the case in the thermodynamic limit when the system is extremely large. And then when I went right beyond it, it would drop back down. So this is the transition. This is a transition point between two phases. Well, what are the two phases? Well, one phase here where the temperature is low, all the spins are pointed in the same direction. This is ordered, completely ordered. But over here, where the temperature is high and we're shaking it, it is very disordered. So it's a transition from order to disorder in this particular model. It's a phase transition. And we will argue that right in here is where interesting complex phenomena emerge, collective phenomena emerge. Those pulses traveling around on the array. And what we need to do in order to see that is to get at this critical temperature. We need to take the control parameter and bring it into a special range. So one comment about this, if this serves as a model for the brain, if the brain is really kind of right here where it's interesting, you don't want this, right? Your brain would be bad if it was disordered. Maybe tonight, late tonight, your brain will be very disordered. Maybe if you have a seizure, your brain will be very ordered, all the neurons on at the same time. But normal operation, something like this. If this is really what's going on in the brain, you will notice that this has to be just right. You have some control parameter, and it has to be within a very narrow range for it to operate in this way. That is one of the main problems with this idea of the brain, is that you have to have potentially special tuning to allow this to be in the right spot. And one of the big mysteries is, if the brain is like this, how do we get this in the right spot? Now with the brain, the control parameter is not your temperature. It's not like you go running outside and your brain heats up. It's not that. It's something else we will talk about later. But for this model, temperature is the control parameter. Okay. All right. So that's what happens with the correlation over distance as we plotted. Now I'm going to change the axes. I'm going to now plot the log of the correlation against the log of the distance. And what you see here is something that looks almost like a straight line. This is a very tiny little model, but it looks almost like a straight line. And very often, many people in this area, I think too often, they draw a straight line and they go, power law. We have a power law. Ha-ha, that means everything is very interesting. And I'll talk about this more later. But for this model, you will get a power law. That means it's a straight line. If I made it infinitely large, I really would get a nice straight line if the model was very big. And what that means is that the correlation length scales as the distance between lattice sites raised to some negative exponent. That negative tau is the slope of this line right here. That gives us this, okay? That's a power law relationship. And in physics, we often are interested in power law relationships. Now, power laws are something that you should expect to see when a system is critical, but there's a long story behind that, and I'll get to it in a few minutes. So it is one of the things that suggests, but does not prove, that you may have a system that is critical. Okay, this would be what it looks like if I had an infinitely large model like that. Okay, and if the system was not critical, I would plot the correlation and it would go down away from that, like there, okay? And one more thing, if I take the expected value of the correlation length, if I take the probability times the distance at all distances, I take the integral of that, that value will be infinite. So the integral, or the area under this, diverges, okay? So the correlation length, what that means is right at the critical point, there is some probability that some lattice site will be able to communicate with another lattice site even infinitely far away. Some small probability. So there can be communication across all scales. It is not just a hierarchy, one thing telling everything down below. All scales can communicate. That little one can communicate to everything else, or everything else can communicate to that little one. Very weak. Yeah, I would say you have to do it this kind of way. And you would, what you will get is it gets weaker and infinitely weak as you go infinitely far away. But it still is above zero. So if you were to take the chance and take its standard deviation, something like that, you should get something that is above zero, or above the standard deviation at all distances. Now, you would have to run this simulation for a very, very, very long time. But at least analytically, it will be above zero. That's a very good question. But yeah, I mean, right, but here what happens is this is a small simulation. It's only, I don't know, 30 by 30 or something like that. If I'd make it bigger, what happens is this thing goes out further. And the limit, what you can do is find out how does this point here scale with the size of the simulation, and what you would find is that this would go to infinity with the size. Yeah, excellent question. Are you a physicist? Ooh, gold star. Do we have a gold star give you? Very good. All right. So you're thinking about it. I like that. It's hard to do early in the morning, huh? Okay. Okay, so non-critical like that. All right, so two main things from this tutorial on criticality. One, something like this. First, you get an optimum point. Right when the control parameter is just right, you get this function that points up. So if we are talking about communication, the ability to communicate goes up. Later on, we will talk about the ability to store information, or we will talk about computational power. The idea is that the brain has some parameter, and when it's in the right spot, it'll go up. So when things are critical, you will have this optimum function. Another thing is that very often you get power laws, but I will tell you more about that. So those are the two main things I want to communicate to you about criticality in the Ising model, and that will help us in understanding some of the neural data. Any questions on this part so far? Seems okay? So you'll do fine on the homework I give you, right? Okay, we'll see later. You can ask me later. All right, now I want to get to the neural data. What does the neural data tell us? I mean, so what? That's a model of a piece of iron. Is our brain just a magnet? Is that all? You know, is there something else going on here? All right, so here's work that I do in collaboration with Alan Littke. He is at UC Santa Cruz. Actually, he lives at CERN, the particle accelerator, Geneva, Switzerland, and he built silicon strip detectors for the collider halls where the proton-antiproton collisions happen. And he built these devices, these silicon strip detectors, and then a little over 10 years ago, someone said, hey, these are really neat devices. You could probably grow neurons on them, and we could record with very good resolution. And so he decided to modify them, and then we were able to record from neurons. Here's a piece of brain. This is cortex taken from a rat. It's been cultured in this case, and we put it on this electrode array. I don't know if you can see from there, but these are 512 electrodes. They're put closely together, and the distance between these electrodes is 60 microns. So the average cell body size is about 10 microns. The dendritic arbors of the neurons go for maybe 200 microns, something like that. So on one of these electrodes, we get signals that look like this. We get lots of noise, and then we can get spikes, individual neuron spikes. Sometimes we get more than one spike. There we go. So we get more than one spike, and typically what we get is we are able to identify the shape of this spike and its amplitude. We see it not only on this location, but we see it on 6 or maybe 7 or 8 locations around us. So we have many copies of that spike. If there is any neuron in between here, we can easily pick it up. We think that we are sampling all the neurons that spike within that area. The thickness of this culture is about 100 microns. So that's about this distance here. So the height of the culture, it's a sheet of neurons. The height of the culture is not bigger than the distance over which we see the electrons, or the neurons. So we do not think there are any neurons above us. We think that within this area, we are sampling almost everything that spikes. Now, that does not mean that there are neurons in here that we do not hear. There are probably 20,000 neurons in this area. When we record, we get maximum 700. What's happening to all the other neurons? Are they spiking, but we don't hear them? I don't think so. I think they are not spiking. They are quiet. There are many, many neurons that are quiet in here, that spike maybe once in the whole hour. We can record for 8 hours if we want. So we are able to sample very, very much of the detail of what's going on here. Let me show you really quickly a simple little movie. Every blue dot is a neuron activating an electrode. This is only 100 milliseconds of activity. So we get lots of neurons spiking. We get this for up to 8 hours. We get up to 700 neurons. I think our average is about 350. So we have a very, very nice electrode array. It used to be the best in the world until I think an Italian group a couple years ago, they built one with 4,096 electrodes. So they make us feel like nothing. we are nobody now. But still, it takes a long time to get the software to work. So they are still a few years behind, and I hope that in the next 2 or 3 years we can publish papers on this, because after that I should retire and move to Recife, right? So anyway, we're trying to get as much as we can out of this. All right. So let's do some very basic statistics on this. So when I showed you that movie, there were sequences of activity like this. And so one thing we could do is we could say, let's look at places where we had consecutive activity like this. And there was a blank at the beginning and a blank at the end. Maybe these are like words. You know, there's quiet, quiet, and then brrrt, quiet, quiet, brrrt. So what we can do is just count the number of neurons that are active. So here the sequence size is 11. You know, 1, 2, 3, 4, 5, 6, 7. You count up to 11. Okay? I can count the size of it. I could also count the length of it. 1, 2, 3, 4, 5. 5 time steps. We pick a time step of 5 milliseconds. That's about the time it takes to shoot a signal from one electrode to the other. So that's about the temporal resolution. So we can do statistics on the size, the number of neurons, or the duration, the length of it. Now, again, I go to a log-log plot. This is in powers of 10. This is the probability of a certain sequence of size S. This is the sequence size. And I count the number of spikes in one of these sequences. If I take the data and I randomize it, if I just shuffle it in time or shuffle the electrodes, this is the type of plot that I get. Very rarely will I ever get a sequence size of about 10. So very rarely will you get 10 neurons together, almost never. Okay, this is what you would expect by chance. What we get in the actual data is something that looks like this. So it seems to look like, approaches a straight line. So it looks like a power law, like we talked about before, where the probability of a sequence of size s scales as s to some negative tau, like that. Okay, so this was something back when I was a postdoctoral associate working in Dietmar Plenz's lab. I was very excited about this because I thought, oh, well, maybe this is something interesting. And so we published a paper in 2003. We called these neuronal avalanches because if you look at sand piles, if you take a pile of sand and you drop little bits of sand on it and you look at the size of those cascades, that also follows a power law like this. So those were sand pile avalanches. So we thought that we would call these neuronal avalanches because they had the same statistics. Now, this original work we did was with something called local field potentials. And I will get back to this later. But that original work did not look at individual neuron spikes. This data does look at individual neuron spikes, identified neurons. This is a little piece of brain that's stuck on a piece of filter paper and then given culture medium, and it grows for 2 weeks in an incubator. It does not look at anything outside. It has no sensory input. It is not being stimulated. So it's spontaneous activity. Now, when we first did this work, these were cultures, and it was spontaneous. Since then, people have looked for these things in awake behaving animals, in sleeping animals. Siddhartha has a paper on that. And I'll talk a little bit about more people. People are now looking for these things in humans. So there's a lot of data finding it in the intact brain. But this was like the first time we looked at it. And yes, that was one of the big problems. They go, this doesn't matter for the brain. This is a little piece of tissue in an incubator. Who cares, right? So, and, you know, that was a valid criticism, but it's taken many years to show that it is not limited to that. So yeah, it's just spontaneous activity. We can also stimulate. And we have not looked at the statistics for that, but if you make it quiet and then stimulate, that would be an interesting question. Does it also produce a power law of avalanche sizes? So yeah, there's some data that people get this in humans. This is work by Viola Priesman and colleagues. And what they did is they were able to insert electrodes into humans, something that my university would never allow. These were epilepsy patients, right? So patients who have very serious seizures, they want to stick the electrodes in and find out where the seizure might be starting from. Where is the focus of the seizure? And I will give you guys these slides afterwards. I will post it on a little thing and you can have all the slides. So this is very interesting work. Here they recorded things that are like field potentials, but there is also work of spikes in humans that looks at this as well. And what they find is something a little bit like this. They have, I think they had 64 electrodes maximum, and they get things that look like this, and then it falls off. It's going to cut off somewhere near the size of your electrode array. And the hope is that if you had a very large electrode array, this would keep going. And then they get slightly different results for whether the patient is awake, in REM sleep, stage 2 or stage 3 and stage 4. You get slight differences. So you get it both during awake and asleep. This is with field potentials. So there's been a lot of work showing that you can get some of these things in humans as well, or at least suggestions of it in humans. This is still an open question. So, I mean, my main point in raising this is just to say that there is some work that is similar to what we find in a culture, also in humans, also in cat, looking at cat spikes. Dietmar and Wolf-Singer have worked on that. So there's lots of papers since then looking at all of these things. I mean, now it's almost embarrassing where people are finding it. They're even finding it in leech ganglion. And if I was to say where a power law, I would say no, not in leech, but no, you get it in leech. You get it lots of different places. So we do not know why this is, and as I will mention in a few minutes, some people think it is an artifact, and that is something we need to address as well. So this is a hypothesis. It is not proved. So, and I am open to feedback and questions. Okay, so similar types of data are being found in humans. Here's the criticism. And a lot of this criticism came when I was an assistant professor before I got tenure. So it made me very, very scared. I was like, oh no. So here's one of the criticisms. So Alain Destèche and Jonathan Tabol, they said, can power law scaling, can you get these power laws just from stochastic things? Okay, what do we mean by that? Okay, so they get a plot. See, this looks like a power law, right? That is just a random process. So let me describe a couple random processes. Let's just say we take, here, I can use the marker for real now. Okay, let's say we take some random process. I take a coin and I flip it. I can get either heads or I can get tails. Every time I get heads, I go up like this. Every time I get tails, I go like this. And so you get things that look like this. It'll cross, okay? If I take the area under here, like this, if I take these areas they will follow a power law, okay? If I take the return times, the time from here to there, these times here, these will also follow a power law. So whether it's the area or that, they'll follow slightly different power laws, but you'll get power laws. This is a random process. Power laws, easy to get power laws, not that hard. So these criticisms say, so what? You get power laws in your brain slice. Who cares? It's just a random process, like this, right? Let me tell you another thing that produces power laws. Let's say I take a stick and I crack it somewhere randomly. And then I take the two fragments and I crack them randomly. And I keep doing it again and again and again. The distribution of stick lengths will follow a power law. So that's called successive fractionation, okay? If I look at the size of craters on the moon, things that come in and hit the moon and impact it, that follows a power law. Maybe because of successive fractionation. Some meteorite comes in, something hits it, it fractionates, breaks up again. The crater sizes will follow a power law. Many ways of getting power laws. If I have some process that exponentially grows, and I terminate it at some kill time that follows a negative exponential, that will follow a power law. Very common, okay? So this is serious criticism. How do I know that I don't have something that is really just random? So here are some examples of things. If you plot the rank of a word against the word frequency, so let's say in English language the word, let's say the, it gets a rank of 1, and then how often it occurs in a sentence will be the frequency. The, a, and, things like that. Other words like, say, football in English don't appear very often, okay? So what you have is the rank, the power of 10 of the rank, and the word frequency. It follows something like a straight line. This is called Zipf's law. City sizes also follow this kind of thing, slope of -1. You look at citations, you see something like that. The tail of it follows a power law. Web hits follows a power law, something like a power law. Books sold, telephone calls received, earthquake magnitude. Now some of these things, like say earthquakes, might be critical, but some of them probably are not. This happens not only in English, but probably also in Portuguese, Japanese, any language that has been looked at. Is language critical? Is it balanced at a special point? Ooh, what should we do about that? So this is a paper by Mark Newman in 2005. So many things have power laws. In fact, it's like a Gaussian distribution of the 21st century. Everybody's got one, right? It's not that hard to get. You want something else. So, if you really want to demonstrate criticality, you must do more than just show a power law. Here are some of the things that you should do. You should have multiple power laws. You should have something called a scaling function, and I'll tell you about all these things. You should have an exponent relationship. And you should also have something that shows different phases, okay? You should be able to take it from order to disorder. Somehow by moving that control parameter, you should be able to move the system from one thing to another. Okay, let's go through these things and let's see if the neural data have these signatures. Of course, I wouldn't be telling you this unless they did, but let's go through it. Multiple power laws. So first, let me explain why in a critical system you should get a power law. Why does this happen? Okay, if you go back to the Ising model, that model of a magnet, remember there was some critical temperature where the function went up like this. Let's call this the critical temperature. If I am near the critical temperature at some other temperature T, I can represent some other variable, let's call it epsilon, by this. So when I'm right at the critical temperature, epsilon will be 0. When I am near the critical temperature, epsilon will be very close to 0. Okay? If I really have a phase transition, then what happens is I have a reduction in dimensionality right near the phase transition point. All of the properties that change phases will become dependent on one variable, and that variable will be the control parameter. In this case, it will become temperature. So if I have any function of state, whether it's the correlation length, or something called the susceptibility, or something called the specific heat, all of these things, many different properties, they will be able to be expressed as expansion of powers, like this. So let's say I have some function, let's say it's the correlation length, I can expand it in terms of my variable epsilon, like this. Okay? If I have a phase transition, and if that state function depends on the control parameter. Now what happens when this temperature is very, very close to the critical temperature? Maybe I can never get there exactly, but what happens when I'm close? When I'm really close, all the higher order terms drop out. And the only thing that matters is the first order term. That first order term gives us a power law. That's why we get this power law right near the critical point. If I go away from the critical point, if epsilon is very big, then these additional terms will have to count, and then it will not be a power law. It will curve down or curve up or some other function. It makes sense? Is it okay? All right, so this is why you should get a power law in a critical system. And this is work that's been very well documented. You can look at Stanley's book on phase transitions. Nigel Goldenfeld has another good book. So does Gerardo Ortiz, my colleague at Indiana University. So, do we get multiple power laws? Well, yes. We get a power law for the systems, for the avalanche sizes. The avalanche sizes scale as this. What I haven't shown you, but it's also there in the data, is there's a power law for the duration, for the time it takes before the avalanche dies out. It scales to another exponent, minus alpha. And yet, then there's one more power law, which is the average size of an avalanche for a given duration. That scales as the duration raised to some other exponent. Don't worry about all the Greek letters here. Just imagine that as one exponent. That 1 over sigma nu z is really like one exponent. It can be broken down into components. So do I have multiple power laws? Yes, I've got multiple power laws. Would you get this with successive fractionation, where I break the stick and break the stick? No, you would not. You would only get one power law. Would I get this? Well, here, yes, you get multiple. Okay? Here you get it for the area, and you also get it for t. But we have to satisfy all of these criteria. Okay? So here's a plot of the average number of neurons that fired for a given avalanche duration. And here is the duration of the avalanches. And what you get is some sort of thing that looks roughly straight. It's biology, it's not perfect, but it's approximately the duration raised to the 1.3 power. So that's just another example of a power law. So I'm just giving you an example to say that we've got multiple. Okay. The other thing we have is a scaling function. Let me describe what that is. If you go back to this sequence like this of a single avalanche, and you were to plot it as it unfolds over time, you could get something like this. So here are the different time steps in 5 millisecond frames. Now I plot the number of spikes at each time step. So there I've got 1, here I've got 3, there I've got 4. So it goes up and then it comes down. We'll call this the avalanche shape, or some people call it the avalanche envelope, something like that. So here's a question. Do all the avalanches on average follow that same shape? And if they do follow that same shape, are they just copies of one another at different scales? And if that's true, then the dynamics of how the process unfolds on the network will have a scaling relationship. So we'll call this function here little s. So it is going to give us the shape at every particular time for a given avalanche duration. So here, this avalanche duration is 1, 2, 3, 4, 5. So for a duration of 5, at time step 1, 2, 3, 4, 5, I can tell how many neurons are activated. Okay, so now, if I were to just take the area under that little shape, under that little parabola, if I take the area under that, that will give me the size of the avalanche for a given duration. Okay? So I get something like that. So if that's the case, then what that means is if I take the derivative of this, I undo the integral, I take the derivative of it, and what I said before was that this followed this scaling relationship. If I take the derivative of this, then I should take the derivative of this. Taking the derivative of this gives me a -1 for the power. Okay? So then I should say that every single avalanche will scale as a function of its duration raised to this power times some other function that will give me the shape. This thing is the universal scaling function. And here I will always divide the duration by the maximum duration, so this thing will only have duration from 0 to 1. It will only give me the shape. So what I'm trying to say is this particular shape expanded or magnified by this power will give me every particular shape at every particular time. I'm saying that this is the universal shape of all the avalanches that will propagate in this system, and that it will have a scaling relationship. So that is something that should happen when you have a critical system, and will not happen when you have a system that is not critical. So let's look at the data. So here is an example from the data. So here is the number of neurons that fired, and here is the duration of the avalanche. And now what we did is we took all avalanches of duration something like 70, and here's what we get, and those are the error bars. All avalanches of duration 90, for example, and all avalanches of duration 110. So the question is, are these things really just copies of one another? If you look at it, it looks like they are. But what we want to do is see if they all line up on top of each other if I get the exponent from another power law, and I take that exponent and use it to resize them, will I get this to collapse? And the answer is yes. And what we have done here is I have taken the average number of firings and I've rescaled it by this exponent, 1 over sigma nu z. That exponent I got way back here. That exponent was extracted from this plot. So this plot here gives me the exponent that tells me how I should resize the heights. And so they collapse. So I get something like this. So this is a paper we had in 2012 in Physical Review Letters, and this is then the universal scaling function. It tells us something about how the avalanches unfold on the network. It tells us that they start out at a certain level, they peak, and then they die out. Now, the rate at which they do this also tells us something, and I will explain that in a few minutes. But this is very informative because it tells us about the dynamics, how it unfolds over time. So there's the exponent there, and that's how it comes out. So that's the universal scaling function, this is the exponent there, and this is the function of the avalanche size at every given time. Okay, so this is another thing that tells us we probably do not have some stochastic process. We probably do have a process that is actually critical. This actually, it has since appeared in the Journal of Neuroscience, I think. This is Roberts et al. This is work by Michael Breakspear and his group. What they have done is they have taken advantage of infants that had hypoxia. So in a hospital, some of these infants do not have enough oxygen. And so as they come back to health, they have bursts in their brain of activity. And they look at these bursts of the brain, and what they show is that these things follow something like this, and you can basically collapse them. Here, this was done over something like 3 orders of magnitude. So you've got very good human data that shows avalanche shape collapse. They also have an exponent relation, like I will show you in a minute. So this suggests that, at least in not completely healthy babies, you can also see this kind of thing. Now here's the last part, well, the next to last part. here is the exponent for the avalanche size, the slope of that power law. Here is the exponent for the avalanche duration, and this is the relationship of the size for a given duration, the exponent for that. What this says is there should be a relationship between these exponents. And this just basically is a matter of geometry. This has something to do with the height. This has to do with the height. This has to do with the size and the duration. So the duration, the total size, and the height are all related to one another, as you can imagine. So that's the avalanche size distribution exponent. That's the lifetime distribution. And that's the exponent for height rescaling. So when we put in the values that we observe experimentally, we get decent agreement. It's not perfect. There are some error bars on this. And we don't always get it. There are some tissues that do not show criticality. But many of the tissues do, and we now have data that shows this in vivo as well. We've done recordings in rats with wire arrays, and we get this. So we think that it is a reasonable thing to find, supporting criticality. Okay, there's one more thing. So what I have shown you so far is we have multiple power laws. We do have a universal scaling function. We have an exponent relation showing how these exponents are related to one another. And the last thing is, do we have different phases? So here's some data that we took from a 60 electrode array. This is field potential data. You can show the same thing with spikes, but this shows it fairly well. Here is the activity in a regular slice. We've done nothing to it. It seems to follow roughly a straight line, and then it cuts off somewhere close to the size of the electrode array. So you get something like that. If we put picrotoxin on it, this blocks the inhibition. What we get is something that distorts from a power law. Now we get a hump that builds up down here. Here what we have is many avalanches that are basically the size of the whole array. So we get a different type of activity. Here, lots of big avalanches. If we put CNQX on, what we get is this thing begins to curve downward. So we get more small avalanches. So we're able to control this. We're able to control where this thing is by changing the balance of excitation and inhibition. Other people have also shown this as well. Sergio Martinoia's group in Italy has shown this. Question? Yeah, CNQX blocks glutamate receptors. And so now you don't get excitatory transmission. So sometimes people put CNQX and AP5 on it to block also NMDA receptor channels. So if you block excitation, this will curve down. And if you block inhibition, this thing will curve up. Here you get small avalanches. Here you get many big avalanches. Here you get avalanches at a variety of scales. Why should you care? Okay, so we proved that the neural data, or at least strongly suggested that the neural data really do follow a model that has a tunable critical point. Well, why does it matter? Who cares at all about this? Okay, so let me tell you some implications for this. Let's talk about dynamic range. So Morrow is in the audience. He's published on this quite a bit. What is dynamic range? Well, here particularly, you have, let's say at night you go into a room, it's very, very dark. Somehow, after a few minutes, you're able to see where the desk is and where the bed is and where the bathroom is. Your eyes can adapt to very small numbers of photons. What about you go out on the beautiful beach? Huge numbers of photons coming in, right? Many orders of magnitude more. And yet you're still able to adjust and then eventually see. Our sensory systems have a huge dynamic range over many orders of magnitude. How in the world can they accomplish this? This is a very difficult thing to do. Well, the dynamic range describes how many orders of magnitude you can make sense of your information over, how many decades. So let's say we have some neural system that looks like this. We can measure a response here, and we can give a stimulus here. When the stimulus is very weak, we'll get almost no response. And when the stimulus is very strong, we'll get a lot of response. Usually what this will do is follow some sort of sigmoid function. Right in here is where you get the largest range of response for your stimulus range. So what we can do is we can quantify this. Let's go from the 20% response all the way up to the 80% response. And the stimuli over which you can make this out, this will be the approximately linear portion of the sigmoid curve. This we'll call delta. That will be our dynamic range. These are just definitions from sensory psychophysics. So it makes sense that what you would want is a very large dynamic range. You want a system that is able to have a big dynamic range. Okay, now here's some work. This is a figure from Dante Chialvo's News and Views piece of Mauro Capelli's paper that appeared in Nature Physics in 2006. And it illustrates nicely the main findings of the paper, and Mauro can probably explain more in the next lecture. But very briefly, imagine you have sensory input and you want to get some output. And these are different networks. Here's a subcritical network, a critical network, and a supercritical network. If the network is subcritical, then what happens is I have very weak connections. I put something in, and that activity will quickly die out. It will be damped. And so I put in lots of stuff, and I only get one thing out. So it's very, very weak in the response. Now, if I put in a tiny bit, I'll get nothing out. But even if I put in a lot, I'll only get one. So it only ranges from 0 to 1. Very little delta. Okay? Let's take this case. It's supercritical. Here we have very strong connections. Everything I put in is amplified. And so now, if I put in 1, I get out what? 1, 2, 3, 4, 5. I get 5 as an output. If I put in 2, I get 5. If I put in 4, I get 5. No matter what I put in, I get 5. Dynamic range is very little. It's always 5. Maybe it goes from 4 to 5. So the dynamic range is only 1 here. Dynamic range is only 1 here. What about when you're at the critical point? Here the connections are approximately 1 to 1. So if I put in 3, I should get out 3. If I put in 5, I will get out 5. If I put in 1, I will get out 1. It's not amplified and it's not damped. And so now I have a dynamic range from 1 to 5. And so here if I plot the dynamic range, what I get is a curve that looks very much like what we saw before. It's something that peaks right around at the critical point, something called a branching ratio that Mauro, I'm sure, will explain later. But basically, it is a tunable system. When it's low, you get very little dynamic range. Right at the critical point, you get a lot. And so now, how can our senses respond to many decades of input? Well, if they're operating near a critical point, they have optimum dynamic range. And this paper has since been followed up by experimental work. It's not often that theorists in biology actually predict what will happen. And the experiments actually proved Mauro and Canucci to be right. This is work done by Dietmar Plenz and Woodrow Schuh. And what they showed was this exact picture is what you find in a tissue. When you tune it to be subcritical or supercritical and you stimulate it, you see exactly this kind of function. And so this is a figure from their paper. Basically, this is the size, and this is the stimulation. So when it's subcritical, this is delta. When it's critical, this is delta. And when it's subcritical, actually, I think I got it wrong. This might be supercritical here. You get something like that. And so what happens is, this is a bigger arrow than this one or this one. So right in the middle is where you get the maximum dynamic range. And so if you plot the dynamic range delta as a function of a tuning parameter, what you see in the data is something that goes up and then it comes down. And here they put on picrotoxin to block inhibition. Here they put on DNQX, which is like CNQX that I showed earlier, and AP5. This blocks excitatory transmission. This blocks inhibitory transmission. So on either side, you can make the system have less dynamic range when you tune it away from the critical point. Incidentally, this is another example of the idea that you really have a phase transition. Very nice work that shows that. Okay, so dynamic range is optimum at the critical point. What else can we say? There are other things as well. If you were to look at information transmission, you want to send information through the network, that also shows a peak. All I'm going to show you is a bunch of functions that look like this. They just point up. Information transmission, that's a simulation. It's since been confirmed by Schuh et al. In experiments. This is information storage. This is a paper that basically shows the number of repeating patterns is maximized near this critical point. So you get a function that goes up and down. This has not been shown experimentally yet. People are working on it. This is a paper predicting computational power. This is the exact figure from their paper. But basically, this black line corresponds closely to the area of darkest shading. And if I reinterpret their figure, it's basically another one of those figures that looks like that. Yes? Ah, very good. A guy from IBM asked me, how is computational power defined? So, very good question. All right, so to explain this here, how do they define computational power? What they did is they took a model. So this is simulation work. They take a model network, and they can tune it to be subcritical, critical, or supercritical, okay? And what they do is they feed it some input, some temporal input to all the nodes, and what they do is they get an output, okay? They randomly pick a Boolean function. You feed some inputs, you get a Boolean function, AND gates and NOT gates and NAND gates and everything, and you get some output here. Their goal was to mimic the Boolean function, okay? And they wanted to mimic the Boolean function by taking activity from this reservoir. So they sample all the activity in all those neurons, and they adjust the weights, and they have a single threshold unit as the output. They want to adjust those weights to mimic the function of this Boolean, randomly chosen Boolean function. And they find that when the network is subcritical, it's just random activity. No matter what functions you try to compose based from this reservoir, you cannot mimic the Boolean function. When it's supercritical, basically there's only one function. Everything turns on. You again have a limited basis set. When it's at the critical point, you've got many things going on. You've got AND operations, OR operations, NOT, and things like that. Exactly. It's liquid state. Yeah, I didn't know if everybody knew about that. It is exactly a liquid state machine paradigm. How many people have heard of liquid state machines? Echo state networks. Okay. All right. So I'm glad I explained it. So what you do is you take some bunch of neurons and you just sample from them. The idea is that if I sample from it and I find the right things in there, I can put them together to mimic any kind of computation you want. So somewhere in that big mass of neurons, there's an AND gate. I just have to find it. Somewhere there's an OR gate. I just have to find it. Somewhere there is addition and subtraction. So what I do is I have lots and lots of lines that come up here, and then I train it for a little while, and I find out which line is giving me what. And now I assemble them in the right way, and I can get an output of almost any desired computation. That's only if this reservoir has sufficient diversity. If it is not diverse, I will not be able to compose these functions. That's the idea behind liquid state machines. And so what these guys do is they tune a reservoir for a liquid state machine, and they find out that they fit the maximum number of Boolean functions when it's right at the critical point. Okay, and dynamic range, yes, Canucci and Capelli, demonstrated by Xu et al., and I just mentioned that. Okay, so for lots of information processing functions, you will have this kind of optimum point right at the critical point. That's why it might be useful for the brain. That's the theory. It is not proven. It's a hypothesis. There are many people, among them my grant reviewers and paper reviewers, who disagree with this idea. and this is good. This is how science should proceed, though. You propose an idea, you say, hey, I think it works this way, and there's always someone who comes out and says, I am skeptical. That's good. We want to be skeptical of things. We want to always test our ideas. And if it does not follow or survive the test, then I should abandon the idea. I should not be religious and hold to it no matter what. I should let it go if I am a scientist, okay? And I think it's an interesting idea. I am fortunate and happy that many people find it interesting, but if it is proven wrong, I need to let go of it, okay? And right now I would say it's kind of, who knows? Maybe another 10 years we'll know one way or the other. But it's what? It's on the border. It's right on the critical point. It's tottering, yeah. And you could help. No, I don't want I want you to decide on your own what you think. Okay, so one more thing. In terms of what does this tell us about, does it tell us anything more? Okay, maybe it's optimal, but does it tell us anything more about the network, how the network is connected? And what I will say is this. We are able to measure network connections using something called transfer entropy, and I can speak more about that later if you want. But if we take those connections that we observe in the data and put them into an integrate and fire model, if we put them in and we run it, what we find is that we get avalanches that look like this, and we get correct avalanche shape collapse. So we get the right exponents if we get the connectivity from the data. So that is all encouraging. It looks good. However, if we connect all the neurons to all the other neurons, we do not get the correct exponents. We get different exponents, okay? So that suggests that these exponents may be telling us something about how the network is connected. So let me explain that. If we go back to that exponent relation, imagine I had something like this. Here I plot the average number of neurons that fire for a given duration. And on the bottom, I'm plotting the duration like this. Let's say I had a power law or something that approached the power law that looked like this. Here is 10 to the second, here is 10 to the second. So this exponent here, it must be 1, right? It must be t to the 1. So the number of neurons scales as t raised to the power 1. We just get that, okay? What does that mean? That means when an avalanche occurs, its size is exactly equal to its length. Well, what kind of avalanche would that be if the size was exactly equal to the length? Well, it would have to look like this. It would have to be a chain. So when I get an exponent of 1, that means I get a chain. That means the only way these things are propagating through the network is by 1, following 1, following 1, following 1. There's no branching going on. So that exponent tells us something about the structure of the network. Does that make sense so far? Okay, now what happens if we get another different type of result? What happens if I get something like this? Here, I get a size of 100 for a duration of 10. So now the relationship is t squared. So the duration is 10, I square it, I get the size. Well, there we must get something that looks like this. Whoops, go back one. Here we get something that looks like this. Now I have to have some branching that goes on. So here, for 1 time step, the size is 1. For 2 time steps, the total size is 4. For 3 time steps, the total size is 9. So here, the square of the duration gives me the size. That tells me something about how it must be branching. Now, it turns out that this exponent, which I previously labeled as 1 over sigma nu z, it has to be between 1 and 2. It cannot be greater than 2. If it's greater than 2, well, it could be. If it's greater than 2, it is not critical. It cannot be critical. This is the maximum value of branching that you can get in this type of model and still have criticality. If it's greater than that, it will expand too fast and it will not be critical. So the range of this exponent, anywhere from 1 all the way to 2, tells us something about how the process branches. So they indicate structure. If I have an exponent of 1, really, for all practical purposes in the data, I have unconnected neurons. Okay? I could have chains. If I build a model, I could have chains. But in data, you never find something exactly like that. So this would only be if I had random data and I made my avalanches by randomly concatenating things together, grouping them together. If I have an exponent of 2, that means I have all-to-all connectivity, and branching proceeds in that way. But what we actually find in the data is something like this. I get an exponent of 1.3. So I'm somewhere between unconnected and all-to-all. This tells us something about the dimensionality of the branching process. So that's another reason why this is useful. It tells us something about the structure of the network, the functional connections on which these avalanches spread. And if I go back to the local field potential data, this is the stuff that I originally did with DeepMOR in 2003. Here's a 60 electrode array. Here's the local field potential. Here's another one. We threshold it. We get data that looks like this. I want to talk about the exponents and what that says about the network structure. We got an exponent of -3/2. That's the slope of this right here. So this is the probability of an avalanche of a certain size. Here's the number of electrodes or the total microvolts in amplitude. So we get -3/2, and if we plotted the duration distribution, we got -2. If I plug those into our exponent relation, what we get, we plug that in, that's -2, this is -3/2, and what we get is 1 over sigma nu z of 2. So what does that mean? That means we must have all-to-all connectivity in the local field potential data. Or in this model, it suggests that. Yeah, Mauro.
Not necessarily all-to-all connectivity, because, these are just mean field exponents, right?
Yes. Yeah.
So a random graph will probably give you that, right?
Would a random graph just give us this? Depends on the sparsity of the random graph. If it's very sparse, it won't give you that.
No, a connected graph. Connected random graph. No.
A connected component. 10 random neighbors.
So it's one graph.
I don't know. I'll have to see. I haven't done it. Have you done this?
No, I can bet.
Okay, we could.
I'll bet.
What should we bet? We'll bet a beer, of course. Okay, you might be right. I actually don't have a strong opinion about it. I think that here's my guess. My guess is that this is going to depend on the sparsity of the network. If it's too sparse, you will not get this. If it's sufficiently sparse to be functionally all-to-all, where basically you can go from one node to almost any other node with a very small number of jumps, then it will be close to this. Yeah, so maybe you're right. Maybe you're right. Okay, so this suggests all-to-all, or with the Capelli addendum, perhaps random. We'll have to see, okay? But sufficiently dense, all right? So what this is saying, is this suggests that the local field potential data, at the very least, is connected in a way that's quite different from what we get for the spike data. Because we always get this for the local field potential data, and we get this for the spike data. So these processes are definitely propagating in different ways. Okay. And so my main point of this part of the lecture is just to say you can extract something from these exponents that tells you about the connectivity. One last thing, and I know you raised this point earlier, you were talking about epilepsy. So we did some data, we looked at epilepsy patients, and other people as well have looked at this. Thilo Gross and his group, Ed Bullmore, Christian Miesel, these guys have looked at this, and they basically show that you don't get critical data during epileptic seizure attacks. And so disease might be a signature or might be characterized by loss of criticality. This is an open question. We don't know yet. It needs to be investigated. The idea behind this is if the brain is really operating at some critical point, you've got a control parameter, and you need to keep it in a special range. So now he gives it uniform random connections. This is the same number of connections. He swears to me it is exactly the same as the previous one. It's just that they are longer, so now it looks like there's more. Now they go to all different locations. Now he'll fire it up, and what you see is it becomes very ordered. It was random previously, now it's very ordered. This is just to integrate and fire. So it's something like an Itzhakevich. Yeah, and refractory period and everything. And now there's a mixture of these two. Okay, so now you have some local connections with an occasional long-range shortcut. This is the so-called small world connectivity. And again, the same number of connections exactly. And now you get something that looks a lot more like the Ising model at the critical point. And incidentally, this also looks like fMRI data in humans, if you look at it over time. So the idea is this is more interesting. It's not just random. It's not boringly ordered. It's something that's interesting somehow. Yeah? Oh, yeah. You can get traveling waves. Yes, absolutely. Oh, yes. Yes. Yeah. No, and funny you should say that because we'll get to that in the exercises in a minute. Yeah, so Guillermo just said you can get still traveling waves even if you have random topology. Yes, you can. All I want to illustrate is that in this particular model, the connectivity can serve as a control parameter to bring you from ordered to disorder and critical in between. Okay, so we can measure connectivity from data. I think I've mentioned something of that. Here are transfer probabilities. And these are just supplementary slides. If I jitter the data, this shape collapse begins to fall apart. Here's another not so good shape collapse. We actually have many better ones than that. If I jitter the data, it falls apart. This is just to say that it's temporally precise, that it really matters within 30 milliseconds. So you need temporal resolution that's very good. And I think I already showed you that. And I just want to thank the people in my lab. These are the people in my lab who did this work. A lot of the work was done by Shinya Ito. He did a lot of the culturing. And Francis Ye. They've done a lot of this work. Karen Dahman is our collaborator at University of Illinois. She's the one who suggested the avalanche shape collapse. Alan Litke is our collaborator at UC Santa Cruz, who has the 512 electrode array that we'll soon be getting at Indiana. Braden Brinkman is someone now at University of Washington who worked with this work. Masanori Shimono is a postdoc of mine. He did a lot of this shape collapse work as well. And Lee DeVille had a model in which we put some of these connections. We've been funded mostly by the NSF, but occasionally by NIH, Mind Science, Keck, Futures, and Indiana University. So this is my lab group. And one of those people couldn't make the lab picnic, so I let him Photoshop himself in. And then I'd also like to thank my family because they put up with my schedule. It's my wife, Sarah, my daughter, Zoe, and my other daughter, Katerina, and this is our dog, Shiloh. And I think that's it. Thank you. How am I doing on time?
You still got like 20 minutes to go if you want.
20 minutes to go. Okay, so I can take some questions if you want, and then the other thing I can do is I can introduce you to the graphical user interface for the homework, and I can show you some of the things that it can do. I could do both. You want to just take some questions first?
Yeah. Maybe we should get some questions. Meanwhile, maybe I can try to transfer to your computer
Sure.
the announcement of your homework.
Oh, yeah, sure.
The
Go
link
ahead.
to your homework. So he has a real homework, okay? And there's a link where you can download the, is it MATLAB code, John?
It's MATLAB code that will produce this kind of thing here.
Maybe you can show it, and then
Oh, okay,
I'll do it later. Okay.
Sure. Okay.
Questions, please.
Great talk. Just a question to do with the avalanches you're talking about. So in the sandpile literature, from where all of this is derived, there's been a lot of work on when self-organized criticality, as observed, breaks down. And sometimes it's got to do with grain shape. Sometimes it has to do with the substrate. And I happen to have worked quite a bit on all of this. But are there analogs in your system where you would, for example, just see an overwhelming extent of rare events apart from just plugging in lots of inhibition? I mean, is there something you can do to take the system to the other state? So if you're skeptical about SOC, how do you go to the alternative, or do you go to the alternative?
Yeah, very good question. So in addition to just changing the balance of excitation and inhibition, the connectivity changes as the cultures develop.
Right.
So this is work by Tetzlaff et al., PLOS, computational biology. What they did, which I thought was very interesting, is they cultured neurons on a 60 electrode array. And they used what's called a dissociated culture. I don't know if you're familiar with this or not. So
Okay.
Okay. Right. So you're an elf, not a... What are the other things? Elves and hobbits. Okay, yeah. All right. So what they do is they take the brain and they remove it, and they digest it enzymatically. So now you've got all these neurons that are floating in fluid, and you pour it out on the electrode array. They randomly connect, but they don't connect at first, okay? So it goes from a state of no connections at all to being over-connected to then pruning some of the connections. So the connectivity is what changes there over time. And it changes as a consequence of development. They are not manipulating it, so to speak. And what they find is that the system is subcritical, then it becomes supercritical, and then it comes back down, and then it lands at criticality. So you make it go through these different phases as a function of being overconnected or underconnected.
But it always stays at criticality, is what you're saying, so that really is the default state?
Does it always stay at criticality? I would not say, no, I wouldn't say that it always stays at criticality. When we do it, we get some cultures that don't make it to the critical point. Right. And what I would say is the stuff that I show is to show that most of the time you get it. But if I, let's say, for example, have a new graduate student, they come in, they do the experiment, it will not be critical. Okay, so if I abuse the slices, if I give them damage, if I do something bad to them, I will not get criticality. Okay?
But normal stuff, according to you,
normal stuff, most of the time, I would at least bet a beer that it would always go to the critical.
Okay, one other very quick point, which is that a lot of your data has power laws of over about 2.5 decades. Is there any way you can make it bigger?
Than that.
Yeah, because I mean, you know the whole story with power laws. Everyone wants 3 plus.
Of course,
so
you really want a very large system.
Yeah.
So what I should do is work with the Italians who have 4,096 electrodes. And now, the other thing is that there's calcium imaging data. And with calcium imaging data, like Raphael Yusti and others, Jason McLean at University of Chicago, people like that, you can get something like 4,000 neurons at a time if you're lucky. The only problem with the calcium imaging data is that the temporal resolution is not so good. Particularly if you have a large number of neurons and you have to scan, your temporal resolution is maybe 100 milliseconds.
Because, I mean, just one thing, just a remark to say that skeptics will say that it could turn to non-critical behavior for a larger system. So,
oh yeah, it might, and that's certainly an open question. That's what we have to look at. Yeah.
Alipasha Basiri, formerly Janilia, now in Vienna, is doing whole brain zebrafish at 20 hertz.
At 20 hertz. 20 hertz, not 20 kilo. 20 hertz. Okay, whole brain zebrafish. Well, see, it's guys like this that I'm in awe of, but I also hate them, right? Because they're going to put me out of business. So that's really good stuff. So what's his name? No, I could talk to him. Yeah. No, that's a very good suggestion. Yeah, so whole brain zebrafish, I don't know, how many million neurons, 2 million neurons, something like that? 40,000. That'd be great. You want to look at something like that. But you want high temporal resolution. Because often, if you look at something like 100 milliseconds, the avalanches can flow together. So, yeah. But that's a good suggestion.
Hello. Maybe it's a silly question, but I want to ask about criticality in EEG, using LFP from EEG. What is the problems, or what could I avoid to manage it?
Yeah, sure. Yeah, there are some papers on EEG and criticality. And the one thing I will say about EEG is it's a bulk measurement, right? So you don't have individual neurons. And in fact, you don't even have a patch of tissue because current travels in loops. So you could have a source here and a sink on some other location. It's very difficult to localize the sources of EEGs. So you don't know. Now, that said, I don't want to say it's terrible data or bad or anything like that. There are probably clever ways to process it, to look at things. And I think that this is a good thing to do. I just don't know how to handle the lack of spatial localization. I think one of the things that Ed Bullmore's group has looked at is phase synchronization in EEG. And they've looked at those intervals. And they've shown that those things seem to follow a power law like what you would find in a Kuramoto model when you tune this thing close to the critical point. However, that has been criticized because Bertus and colleagues have shown that you can get power law synchronization even if you don't have a critical system. So this is another question that's open in the air. So it's making sure I don't visit any bad websites. My children sometimes use my laptop. Yeah. So that's a good question, and I think it is still open. But that is one of the potential weaknesses of EEG is no spatial localization. Yeah, so the first author is Kitzbichler, and I think it came out in PLOS 1 in 2010, maybe. Kitzbichler.
I can send you. It's a very hard name.
Yeah. But Bullmore is the senior author on that paper, Ed Bullmore. But if you go to Ed Bullmore, the problem with him is he's got so many tens of thousands of citations, you can't find the right paper. So Kitzbichler is the first author on that. And then the other one is Bertouze, Bertouze, is the paper that criticizes that says you can still get power law distribution of phase locking intervals without being critical. So many of these things are and they should be criticized. You need to go through the whole thing and try to figure out. Yeah.
More questions? Okay, please.
Well, there is idea about neural Darwinism that we have avalanches that kind of compete with each other. Can you draw some connections between your lecture and that idea?
Connections between neural Darwinism and this criticality?
I mean, how did criticality come into play?
How could criticality come in? Well, I got Gerald Edelman's book many years ago, back in 1988 or 89, something like that. And I read through it, and I thought it was very interesting. But the title of the book is Neural Darwinism. And he has this idea, very briefly, it goes kind of like this. If you look at evolution, right? You've heard of Lamarck's hypothesis that the giraffe has the long neck because the mother giraffe stretches her neck and then the baby will also have a long neck. So whatever you do during your lifetime is inherited. So that's an instructionist hypothesis, that what you do will instruct the next thing. Darwin said, no, you have random variation, you have selection, okay? So Darwin was right, Lamarck is probably wrong. The immune system, people thought, oh, well, how does the body respond to invaders? Well, one hypothesis was instructionist. Basically, it comes in and you construct something that will follow the shape of this. That's an instructionist hypothesis. The selectionist hypothesis is that you have many, many different shapes, one of which fits, and then it's amplified. And again, the instructionist hypothesis was proven wrong. The selectionist hypothesis was right. And so Edelman then comes to the nervous system, and he says, well, it could be this way, that what happens is we instruct our brains how to do what's right by something like a Hebbian rule. Or what Edelman says is you've got all these different input-output mappings already in your brain. And the one that works is the one that's kept, and all the others are then discarded. That's a selectionist hypothesis. So Edelman thinks that if selectionism won in in evolution, if selectionism won in the immune system, it should also win in the nervous system. So that's what Edelman thinks. But he predicted in 1988 or 1989 that the Hebbian rule would be proven wrong. So since that time, Gerald Edelman has been proven wrong. So I think that it looks like there's Hebbian processes going on. The evidence for that is overwhelming. So his idea of neuronal group selection, I don't think it's correct. But the hypothesis is potentially still alive. There's certainly cortical territories that compete. You know, if you stimulate this finger and you don't stimulate that one, then this territory will go over that one. So maybe the metaphor of competition works somewhat. But I don't know how to reconcile this with neuronal Darwinism. I don't know. If you have ideas, I'd love to talk with you.
No, I'm just saying that if you look at functional MRI patterns, then they crystallize in some ways, right? That you, over time, you have similar patterns repeating over and over in brain activation.
Yeah.
So the distribution of whatever activity is governed by some other things that are purely chance or connections, right? Because you.
Oh yeah.
And are there any connections with criticality in that sense?
That I don't know yet. I know this is a good question. I really don't know. Maybe we'd have to talk later to try to figure out.
Yeah. Excuse me. You spoke about the dynamic range in critical systems, okay? But we know as we analyzing the resting state fMRI and the task-based fMRI, we know 90% of brain activity returns to resting state and spontaneous activity, and just 10% of the brain activity returns to the task-based activity. So how do you interpret this small dynamic range by this new scenario that you want to apply in this regard, in this field?
Well, I think it fits pretty well. Maybe you'll have to tell me how it doesn't. I think if 90% of the background activity is what the brain is doing, and that data seems to fit pretty well with this idea of power laws and being close to critical, I would think that maybe that's a default state for the brain. And then when you engage in a task, you drive the network very hard, it might go above critical. That's quite possible. I mean, I don't see a conflict with that. I do think there are some data that basically show that when you become active in a task, it might become slightly, well, at the very least, the exponent changes. The power law goes up. There's also some MEG data. Maybe you've seen this paper recently where as people stay awake for longer and longer periods, the power law begins to creep up like this, and then it has a spike at the end. Then after they go to sleep, it comes back. So I think it's a biological system. It's only going to hover around criticality. It's not going to be exactly pinned at criticality. Yeah.
And it's not so much the variation in the response that you see, but rather how much variation can you put in the stimulus and still get a reasonable amount of response, I mean, within a reasonable range, like what you're describing. So it's your horizontal axis that you should look at to see how large your dynamic range is. So it could still be working. And maybe I'll talk about this later also a little bit, just to show you psychophysical evidence.
What do happen with criticality if the resolution for the measurement is not good enough?
Very good question. What will happen to criticality if the resolution is not good enough? Well, what you will see, as Viola Priesman was the first one to publish on this, and basically what you see, if you undersample the system, you'll see things that don't always look like power laws, okay? So this is a very important question. And actually, you have a paper on this that just came out. What, PLOS computational biology?
I'll talk about it,
Yeah, okay.
Plus one, yeah.
So subsampling is a very good issue. So you've got thousands and thousands of neurons in there. Are you recording from all of them? So what I would argue is that in the local field potential data, because of conduction, volume conduction, you're sampling pretty much all the signals that are there. In this particular electrode array that we talked about, I think we are sampling almost all the neurons that are there. If I take an array and stick it down into the brain, like Siddhartha and colleagues have done, you will subsample. And there you will get something that does not look like a power law. But what they did in that paper, and I think you're on that paper too, right? So what they did in that paper was very cleverly, they took this avalanche size distribution that had a curve, it did not follow power law, but they showed that there was a scaling relationship. And you could collapse them onto one another using certain exponents. So that also shows that it could be critical. So if you have subsampling, you might not get a power law. You could get different shapes. Then the thing to look for is, do you have an exponent relationship? Do you have scaling relationships? Do these things all fit together? So there are many other ways of looking at that. But subsampling is always an issue. Very good point. Yeah.
So John, you only mentioned synaptic plasticity in passing.
Yes.
Can you comment on that? Are there any experiments blocking synaptic plasticity or whatever your comments?
Yeah. Very good. Okay, so synaptic plasticity probably does have a big role in this. So let me talk about two types. First, there's short-term synaptic plasticity. Then there's long-term synaptic plasticity. So short-term synaptic plasticity, let's say you have one synapse driving another. Very often in the cortex, you have something called synaptic depression. So what happens is the first time it goes through, you have a big pulse. But then if you have another pulse very quickly, it's weaker, then weaker, then weaker, and then it eventually doesn't drive it very much at all. Okay? This leads to sensory adaptation. So in the morning when I put on my shirt, I feel my shirt, right? But that response of me feeling my shirt is not powerful during the whole day. It gets weaker and weaker, thankfully, right? I'm not still feeling my shirt. So whatever the input is, we detect the transient, the very beginning of it, and then it gets weaker and weaker. There's a very interesting model by Levina, Herman, and Geisel. And what they showed is that if you have synaptic depression, which is commonly found in cortex, you can get these networks to basically come to a self-organized critical state. So the way it works is this. When first you have some avalanche go out through the network, it activates all these neurons. You get some large avalanche. But the second time you stimulate, many of the synapses are depressed, so now it is smaller. It takes time for them to recover. You wait, they recover. Now you hit, you get a big avalanche again. So there's this interplay between synaptic depression, making the avalanches smaller, and then synaptic conduction, making them bigger. These things eventually balance out. And what you have is avalanches of all sizes. It's much like something called the forest fire model, where the trees burn, and then it takes a long time for them to grow up. So that's short-term synaptic plasticity. That has been shown to be compatible with this idea of self-organized criticality. Now, long-term synaptic plasticity, which is thought to be interesting for memory, long-term memory, that has a lot to do with, I think, the work that I mentioned earlier, the work by Tetzlaff et al. And what they show is in developing cultures, when these synapses are forming, you start out with no synapses, you form many strong ones, and then they get weaker. The system goes from being subcritical to supercritical, then back. And so the synaptic strength can somehow control that. Now, what I know is that if we take these cultures and we stimulate them really hard, we can perturb them away from the critical point. So somehow the combination of strengths probably allows it to be at the critical point. So those are a few comments. One more thing is this. If the synapses do store memories, and if the correct distribution of synapses is necessary to be at criticality, then this puts a very important constraint on learning. If I learn something new, I want to strengthen a new synapse. But strengthening that new synapse may cause the distribution to change. It might cause things to be supercritical. So if my synapses are getting stronger, then maybe I'm going away from the critical point. So I would imagine there needs to be, if this picture is right, there needs to be some way of renormalizing the synaptic strengths. And some people have hypothesized that that's what sleep does. We don't know that yet. But did I touch on it? Okay, yeah. Yeah, good question.
Can I just make a comment? I'm going to be talking about this tomorrow, actually. But we find that even long-term synaptic change leads to observed power laws. So whether it's self-organized criticality or not, I'm not sure. But you do get power law forgetting with specifically that. So I'll be talking about that tomorrow.
Oh,
so,
excellent. Okay, very good. Yeah.
Yeah. Okay. Any other questions? If not, John can help you with your homework.
So how much time do I have? Just a few minutes?
Yeah, we have a couple, like...
Okay, let me just show you this real quick.
5-10 minutes.
So you should have software that's on the computers that basically has this. And you should put it in... You all know how to use MATLAB, right? Okay, so you should put this into your MATLAB directory and just open it up, and I'll try to help out. But let me just show it to you really quickly. The idea is this. This is an array of neurons. This is like a sheet of neurons, and they're active. And then you can get some kinds of activity that occurs on the network. And sometimes you get things like spirals. Other times you get waves. Sometimes you get gliders. Sometimes you get repeating patterns or just bursts at different frequencies. And the idea is that you can change things. And I have a little sheet that explains this. And what it does is basically you can have random connectivity, or you can have nearest neighbor connectivity. You can give it a connection density, anything from 0 to 1. You can give it a range, maximum range over which the connections are. If it's a lattice, this is distance 1. This would be distance 2 lattice sites away. That would be 1.41 lattice sites away, square root of 2. Distance, refractory period of the neurons, what the neuron threshold is, and the probability of spontaneous activity. So these are all parameters that you can play with. And I have exercises where I suggest you start at a certain place and then you change one of the parameters and you see how it alters the activity. So in this particular case, if I'm to run it, let me just run it one more time. What if I change it and give it random coupling, for example, and I give it some connection density that's like this, just as an example? What will it look like? So I just changed the parameters a little bit, and you get very different behavior. So the idea behind this is I just want to give you some intuitive feel for how collective interactions can change in a network of neurons. And these are neural parameters that we all think about. We think about what's the threshold of the neuron, what's its distance of connectivity, what's the refractory period, is it randomly coupled or coupled like a lattice? You can change all these things. And by going through this, you get many different types of activity. Here you didn't really see any pattern, but in the raster, here's time, and here's the number of neurons. I think there's a little over 400 neurons. You see bursts of activity. You can change this period by changing different parameters. And I want you to explore those things, and so it takes you through step by step. But that's basically it. There's many different types of activity modes that are in this space. You probably won't find all of them, and don't worry, you don't need to. But it's fun to just play with a couple of them. I think I take you through spirals, waves, repeating frequencies, repeating patterns, and then there's like an attractor in there where the system is random and then it falls into a particular pattern. So I want you to look at those types of things and make comments about what you think, what parameters govern this. Yeah? No, they're asymmetric. Yeah, okay, yeah. I guess I should explain what the let me briefly explain the model. So the neurons are either on or they're off, okay? And they have connections from one to another. And if the connection is there, this neuron will drive the other neuron. Okay? It's like a cellular automaton. But you can control the connection density. So not all of them will be connected. And they can also be off because of the refractory period. And only a few neurons might be active at a given time because you have spontaneous activity. So that means only 2% of the time a neuron will become spontaneously active. So that's what this is basically saying. So you can control all of these things. So when a neuron is active, it transmits activity to another neuron, and so on. It transmits. When you have, it's directed coupling. It's not symmetric coupling. And when I put it on neighbor coupling, it only connects to things within the lattice at this distance. When I put it on random coupling, space doesn't matter. I explain this in the worksheet. The worksheet that I have, I'll just show you really quickly what's on it, and then we should all get coffee, I would think. So I'll show you this worksheet. Actually, it's going to take a while for this guy to load. Let me just open this. So in the worksheet, I just give you a brief overview of the system. I describe, why I'm putting you through this pain. I show you, I describe what the model is, simple cellular automaton. I describe each of the parameters, random coupling, neighbor coupling, connection density, maximum distance, refractory period, what the GUI buttons do, and then different types of collective excitations. So I give you some parameters to start out with, and then I give you some exercises. I think I give you that many. A through G, something like that. So you can open it up and look at it. And I'll be around. You can ask me questions, things like that, just like real school, I guess. Okay. So that's it. Shall we do coffee? Okay.